Hi there, this is just a quick video to discuss the principle of the conservation of momentum, an extremely important principle in physics and of course in biomechanics. The principle of the conservation of momentum states that the momentum in a system before a collision will be equal to the momentum after the collision. So in order to understand this concept, we first have to understand what momentum is, and we've covered this in detail. We know that momentum is the product of an object's mass multiplied by its velocity. We say that momentum is an object's resistance to deceleration. So in this scenario, we're going to be using pool balls. And here we have our red ball here, and in this case, we're not going to measure the mass of the ball in kilograms because that would be a bit hard to work with and would give us a very small number. So the unit of measure for momentum in this case will be grams meters per second instead of kilograms meters per second. But that's okay. It's just because we're working with a smaller object than we normally would if we were, looking at a human running. And looking at their momentum. So in this case we have the mass of the red ball, which we're going to say is 112 grams, and it currently has a velocity of 0 meters per second. It is at rest. This means, it doesn't take much to work out, that the momentum of this ball is also going to be 0. However, we strike the red ball with our cue ball. Look at that, wonderfully animated there, I'm sure you'll agree. Now, the cue ball, just to make things fun, has a mass of 100 grams, and at the moment of impact was travelling at a velocity of 3.2 meters per second. Now, we know that through the conservation of momentum principle, that the momentum within our little system here, so this is disregarding a lot of other things, I know, it's disregarding the frictional forces between the balls and the pool table, it's disregarding the weight of the balls. This is just our perfect little scenario that we can see here on your screen. We know that the momentum before the collision will be equal to the momentum after the collision. So we know the mass of both balls, we know the mass of the white ball upon impact, and from that we could calculate the momentum of the cue ball at impact, and you can certainly pause the video and do that now if you so wish. But what we want to know, what we're curious to know, is what is the velocity of the red ball after the impact. So we're going to assume that the white ball stays perfectly still after impact, after the collision, and we then want to work out the velocity of the cue ball. This type of collision, by the way, we would call an elastic collision, where two objects collide and either they both move away from each other or one moves away from each other. The other type of collision that we also have is an inelastic collision where both objects move away together. So this is an elastic collision. Anyway, as I said, you can take a moment here if you so wish to pause the video and perhaps try and work out the velocity of the red ball after the collision takes place, and we'll go through a worked example on the next slide. Okay, so it helps to divide the situation up into the pre and post collision situation. So on the left hand side we have pre-collision, and on the right hand side we have post-collision. And we know that the momentum in each system, this is the pre-collision system here, is going to be equal to the momentum in the post-collision system on the right. So we're not so much thinking of the momentum of each ball, but of the entire system. Okay, so both balls basically. So we have the mass of both balls. We know the velocity of the cue ball at impact, 3.2 meters per second. We know the velocity of the red ball pre-collision. So our p value here, p for momentum, is going to be equal to the momentum of the cue ball added to the momentum of the red ball. So because the red ball has no momentum, we're simply multiplying 100 grams by 3.2, giving us a total momentum within this system of 320 grams meters per second. So that is the momentum in our pre-collision system. And we know that this will be the same, due to the law of the conservation of momentum, in the post-collision system. So how then can we work out velocity? And like I say, if you weren't sure to begin with and you feel like you're getting it at some point, do please just pause the video and have a go. So we'll go through this step by step. So first of all, in the post-collision system, the cue ball is no longer moving, so it has a velocity of 0 meters per second. Mass is obviously the same, and we're going to add this to the momentum of the red ball, which has a velocity that we currently do not know. So what does this leave us with? Well, the momentum of the cue ball is going to be 0. So this leaves us with the mass of the cue ball, of the red ball, multiplied by this unknown velocity value. Now we know that the momentum pre-collision and post-collision will be the same. So this p value becomes 320. Oh, that should be 0.0 there. I've made a mistake. I do apologise. That's poor form on my part. So 320 grams meters per second, which is equal to the mass of the red ball multiplied by its velocity. And now it becomes a formula triangle. We simply have to rearrange this equation to make velocity the subject. So we now are dividing up, the decimal place is back in there now, well done me. We have to divide 320 by 112, and this gives us a post-collision velocity of 2.9 meters per second, as opposed to 3.2. And this makes sense because the red ball is slightly weightier. It is 12 grams. It has 12 grams more mass than the cue ball. So there we are. Hopefully that helps. It's a fairly straightforward basic example, but as I say, do read around this topic more, and I hope that has given you a brief introduction into the conservation of momentum and made it a bit clearer.